We'll start our discussion of gases by comparing them to the other two major phases of matter, which are solids and liquids. So when you have a solid, the shape of the solid is fixed. It's not going to vary. And the volume is fixed because it's generally a very rigid structure. A liquid, however, is still fixed in volume. If you pour it into a glass, it will contain a fixed volume, but the shape is variable. It will take the shape of whatever container you pour it into. A gas is variable in both shape and volume. If you put a gas in a small enclosed container, it will take up a small space. If you put it in a large enclosed container, it'll take up a large space. And its shape is, of course, variable according to the shape of the container you put it in. We refer to the liquid and solid phases as condensed phases. They take up much less space, whereas a gas will expand to fill whatever size container you put it in. So gases are very special. They have a low density, and they readily mix with one another. And they mostly consist of large spaces. So this brings me to one of my favorite things I like to say is, if you've heard of people talking about a glass of water being, according to an optimist, it's half full, and according to a pessimist, it is half empty. And what I like to say is that, according to the chemist, the glass is actually completely full. It's full of half liquid and half gas, so it's completely full. All right, moving on. Let's talk about how we measure things with gases, and one thing we measure is the pressure of a gas. The pressure is a force per unit area, and that's the kind of units we use, is force per unit area. And in a container, if you put these red colored molecules or atoms into a container, they will be moving around in the container, and that's what a gas looks like. But they will also be colliding with the walls, and this diagram on the right shows that gases collide with the walls. So I'm going to write gas molecules collide with the walls, and that creates the force. The force of each atom or molecule hitting a wall and bouncing off is exactly the force we're talking about for a pressure. And so if you have equal pressure on both sides of a wall, so in other words, if you have the same pressure of gas inside the container as outside the container, then the wall stays still. But if you have a greater pressure inside, the walls will bulge out because of the pressure, the collisions of the gas molecules inside pushing out. So if there's equal pressure, then you'll have equal force for both the inside and the outside. The molecules inside the container bounce against the walls. The molecules outside the container also bounce against the walls. So let's talk about pressure units. And it turns out there are lots of different pressure units that get used. Oops. Okay, so there are lots of pressure units. All right, so the first one I'm going to talk about is PSI, which is pounds per square inch. So that makes it really obvious you have a force per area. The second one is pascals, abbreviated PA, and that is the SI derived unit. It's actually newtons per meter squared, so there you can also see that it's a force per unit area. So 1 Pascal is 1 Newton per meter squared. Atmospheres are abbreviated ATM. And then we have millimeters of mercury. Okay, millimeters of mercury and torr, which are actually the same. Whatever number you have in millimeters of mercury, you also have in torr. And the final one is called a bar, which is actually very close to an atmosphere. All right, so if you look at mercury in a tube inverted into a dish of mercury, which you aren't likely to do because we don't mess around with mercury in open containers, but if you did, you would see that the pressure of the mercury, or the pressure of the atmosphere down onto the mercury, would give you a height in the column of mercury according to that atmospheric pressure. And at normal sea level atmospheric pressure, the height would be 760 millimeters. So normal sea level pressure is listed as 760 millimeters of mercury because that's exactly the height you'll have of the mercury. Okay, so we can convert between any of those units. And we can use, in order to do the conversion, we use the pressure in any given unit at sea level. So for instance, at sea level, in atmospheres, you have 1 atmosphere, which is also 760 torr, also known as 760 millimeters of mercury. That's equal to 101.325 kilopascals. It's also 14.7 psi, and it's also about a little over 1 bar. So one thing to note is an atmosphere and a bar are very close together, close to each other. All right, but you can use these values as conversion factors. So give it a try to solve this problem. We know that the pressure at sea level is all these values, all these different units. But the pressure on top of Mount Everest is much less than that. It's 30 kilopascals. So you have 101 kilopascals at sea level, and you have 30 kilopascals at the top of Mount Everest. So convert that into pressure in torr. So give that a try and stop the video and then continue afterward. So let's take the number 30 kilopascals, put it over 1, and the conversion factor is just whichever 2 units you need up here. We need kilopascals on the bottom to cancel. Whoops. And that's 101.325 kilopascals. And on the top we want torr, and that's 760 torr. So that's our conversion factor. So multiply and divide, and you'll get 225 torr at the top of Mount Everest. Now we're going to talk about the ideal gas law, which is given in the blue box. PV equals nRT. Okay, so first of all, what do the symbols stand for? P is for pressure of a gas. Volume is V, the volume of a gas. N is the number of moles of gas. And R is the universal gas constant. So that's an unchanging value, and we will use it as 0.082. Now we're going to talk about the ideal gas law, which is a very simple equation that we use to characterize the pressure, temperature, volume, and number of moles of a gas. So the expression is PV equals nRT, where P is the pressure of the gas, V is the volume of the gas, N is the number of moles of gas, R is something we call the universal gas constant. And the universal gas constant is 0.0820578 liters, atmospheres divided by moles and kelvins. And we'll also abbreviate that with fewer sig figs. And finally, T is absolute temperature. In other words, it's always going to be a a positive number, only absolute temperature. All right, so what do we mean when we say a gas is ideal? What we mean is that a gas behaves at the limit that we call an ideal gas. And no gas is actually ideal, but the more they follow these particular criteria, the more ideal we say they are. So one of the characteristics is that the gas molecules must be sparse. And by sparse, I mean lots of space in between the molecules. So there's lots of empty space. Another way of saying that is we need low pressure. All right, and another characteristic we need to be ideal is that we have elastic collisions. When the molecules collide with either each other or with the walls of a container, they need to be elastic, which basically means they're not sticky. Not sticky. Okay, let's do an example problem using the ideal gas law. After a reaction in a closed bomb calorimeter with a volume of 2 liters, there are 88 grams of nitrogen gas at a temperature of 57 degrees C. What's the pressure in the calorimeter? All right, so we have a volume, we have grams, and the ideal gas law has moles, and we have a temperature. So let's see what we have. Let's start with the ideal gas law. And we want to solve for the pressure. The question is, what is the pressure? So we'll solve for pressure, and that would be nRT over V. All right, so we have temperature, but it needs to be absolute. We have volume in liters, and we don't have N, number of moles, but we have grams, and we know how to get number of moles from grams. All right, so let's set up the equation down here where we have lots of room. So we need to convert 88 grams of nitrogen to moles using its molar mass. All right, so then that's our N. R is the constant, which we know, 0.0821 liter atmospheres per mole Kelvin. And the temperature, T needs to be absolute temperature, so we need to add 273 to that in Kelvin, and finally divide by the volume, which is 2.0 liters. All right, and when we do that, we'll look at our units. We're going to cancel grams. We're going to cancel moles. We're going to cancel kelvins. Oops. Cancel kelvins. And finally cancel liters, leaving our answer in atmospheres, which is a pressure unit. And we get 2.8 atmospheres, 2 sig figs, because we have 2 sig figs in all the information given. All right, so make sure when you do problems with the ideal gas law that you use the units in the universal gas constant, and make sure your other units agree with those so that you cancel and get the right units for the thing you're solving for.